Hi everybody. Hope you're all having a good day today so far. Today what we're going to be talking about is representation of preferences by utility functions. Now when we're talking about preferences in utility functions, we're talking about decision making, and in particular we're talking about how decision makers evaluate things. Now I've said several times during these lectures that the three elements or building blocks in modeling decision making are the alternatives, the constraints, and the criterion. Now, what we mean by the alternatives and by the constraints, I think, is probably pretty clear by now. What we mean by the criterion is what does a decision maker use to evaluate the alternatives in order to decide which of the alternatives to choose. So today we're going to be talking just about the criterion, and in fact more than one kind of criterion, and that's going to be the essence of what we're all about today. We won't be talking at all about the constraints, and while we won't be talking explicitly about the alternatives, because the criterion is about evaluating alternatives, we'll kind of implicitly be talking about alternatives. So I'm going to start off here by just mentioning several of the kinds of alternatives in the various kinds of decision problems that we typically encounter when we're doing economics. So the first one here in this list is, of course, the most familiar to all of us as economists, the consumer theory problem, where the consumer is going to choose a consumption bundle from a set of alternative consumption bundles, and we model this alternative consumption bundles as n-tuples in Rn, or as points in Euclidean space, if you like. And so let's actually draw a little quick picture of what's going on there. So this is the familiar picture where here we have Rn plus, clearly in the picture, n is 2. This would be, let's say, a typical alternative, a typical consumption bundle. And then here we have the real line. And we typically use as a criterion, that is, we model the decision maker, the consumer, as using the criterion that's a utility function. So we have a utility function that maps from the set of alternatives, alternative consumption bundles, into real numbers, into the real line. And so that's the criterion that is sort of standard for the consumer problem. A second kind of decision problem that we see in the first microeconomics course in your graduate program, for example, is in the theory of the firm, where the firm is going to choose a production plan from a set of alternative production plans. And again, we model the alternative production plans typically as points in Rn, not necessarily in Rn plus, but as points in Rn, or as n-tuples of real numbers. So the picture looks about like this, although again not necessarily Rn plus. And we model the firm as evaluating those production plans according to, typically at least, according to a profit function. And what's a profit function? It's a function that maps from the production plans in Rn into the real numbers, the amount of profit. So I could write a different letter for the profit function, say pi that we often use, but really the profit function is just another kind of utility function. It's the utility to the firm. So I'm going to continue to use U because I'm going to use U for a generic utility function for all of the decision problems that we're going to consider here. today. So here we have a third kind of decision problem and a new kind of set of alternatives. So it says probability distributions here. So this is where we have a decision maker who is making a decision in the presence of uncertainty. So the decision maker has to choose an action from a set of available actions, but the decision maker doesn't know for certain what the outcome will be from the action that he or she is going to choose. So the decision maker is choosing in the presence of uncertainty or under uncertainty. And so what we model the decision maker as doing here is choosing a probability distribution from a set of alternative probability distributions, a set of alternatives. The alternatives are alternative probability distributions, and those are typically not elements of Rn. They would be if the probability space is finite, but if the probability space is infinite, then things are a little more complicated, and those probability distributions don't fit in Rn. The fourth thing on the list here, it says partitions. Well, that's a situation where the decision maker is choosing an information source, a kind of information to obtain. And so perhaps deciding what kind of information to obtain in order to make the real decision. So it's kind of a two-stage decision problem. Choosing first the kind of information you're going to get, and then using the information to make the real decision. So the decision about the information source, the kind of information to obtain, well, we model information and information sources as partitions, just the kind of thing that we saw in the preceding lecture and that we're going to see more of when we actually analyze information as partitions in a succeeding lecture. So the decision maker is choosing a partition from a set of available partitions. Again, in no way an element of Rn. So a completely different kind of situation, and we have to figure out what kind of criterion to use there. And finally, I've put here strategies. So this is what we would, how we would term the alternatives when the decision maker is choosing in a game theoretic situation. So it could be a game theoretic situation in pure game theory. It could be a game theoretic situation in microeconomics. When we have multiple firms competing with one another and each one needs to choose a strategy from a set of alternative available strategies. So the alternatives here would be strategies, and the strategies, they can be very simple, could be just the elements of some finite, even very small finite set, or strategies can be extremely complex, nowhere near just an element of Rn. So what we can see from all this is that the set of alternatives could be just about anything, various kinds of sets of alternatives, not just Rn. So what I'm going to do here is I'm going to use capital X as our name for the set of alternatives that a decision maker might have to choose from among, and I'll draw kind of an abstract set like this. That's our capital X. This would be, let's say, a typical alternative, whether it's a probability distribution when we're deciding under uncertainty, or it's a partition, or it's a strategy. And again, we typically use a utility function of some sort, or payoff function is often the term that's used in game theory for strategies, a utility function that assigns real numbers to the alternatives in the set of alternatives capital X. So we're going to start off by assuming that the decision maker uses a utility function as his or her criterion for evaluating alternatives. And in the familiar consumer problem, that utility function will be a function on Rn plus, a real valued function. And in the general case, where we're going to use x as the name of our kind of abstract general set of alternatives, the utility function will just be a function, again, a real valued function, now defined in general on the set x. So what are some of the consequences or implications of assuming that the decision maker's criterion for evaluating alternatives is a utility function? Well, the first consequence of making that assumption is actually a remark that we saw in a couple of the preceding lectures. And that is the remark, or the statement that I've named P here, that for any real valued function, and of course a utility function is simply a real valued function, for any real valued function, we always can define a binary relation from the function according to this condition star here. And moreover, that binary relation will always be a complete preorder. And so the star condition, of course, just says that x prime is related to x if and only if the utility function assigns a larger real number to the alternative x prime than it does to the alternative x. And so this tells us that since this is true for any real valued function, this is certainly going to be true for any utility function. And this tells us that any utility function will automatically provide us with a complete preorder that kind of represents preference in exactly the sense of this condition star. That is, we can think of this orange preference symbol, I'll call it, as a preference ordering. And so I'll actually use those terms interchangeably. I'll call this preorder either a complete preorder on the one hand or a preference ordering on the other hand. You'll notice that I've written the utility function in green here, and I have written the preference symbol in orange. And that's because I want to emphasize that these are the two different criteria that we're going to analyze in today's lecture, that we're going to be analyzing the relationship between these two criteria. Now, there's several things we should note about this remark P here. The first thing is that the remark defines a function that assigns to every utility function a unique specific preference ordering or preorder. So let's draw a picture of what's going on here. So let's say that this is the set of possible utility functions for a given set of alternatives. And since the utility functions are just real valued functions, that means that this set of all possible utility functions is the set of all real valued functions on that domain of alternatives. And the notation we have used for that so far is script f of capital X. And so the elements of this set are real valued functions on X, that is, they're utility functions for our purposes here. And now I'm going to use orange exactly as I did over here in this proposition or statement P. And so over here we have, let's say, the set of all complete preorders on the same set, capital X. And so what's going on in this function is that for a particular or typical utility function, this always assigns to that utility function some particular, I guess we'll draw it this way, some particular preference ordering. And this is a function. Let's call this set script R, or it's a binary relation, so I'll use R for this. And I'm actually going to use a shorter, briefer notation for this. I'm going to use a script U instead of f of x, but they're the same thing. And so script U, because this is the set of all little u's, the set of all utility functions. And this defines a statement P over here, defines a function, and I'm going to give that the name pi, and that pi function maps from the set script U into the set R for every utility function, picking out a complete pre-order. And I've used pi here just because this is a pre-order or a preference relation, and so pi seems like a natural symbol to use for this function. So one implication of assuming that a decision maker uses a utility function to evaluate alternatives is that then there will be an associated preference ordering that is also a criterion that could be used to evaluate alternatives. And because of this star condition, we won't be able to tell whether the decision maker is actually using the utility function to evaluate the alternatives or is using the preference ordering criterion. We'll come back to that in a few moments. Now let's look at several additional implications of assuming that a utility function is being used. First is that if the utility function is continuous, then the preference ordering will have strict upper and lower contour sets that are all open sets. The strict upper and lower contour sets will all be open sets, and the weak upper and lower contour sets will all be closed sets. And the consequence of that is that the equivalence classes, the indifference sets, if you like, of the preference ordering, will all be closed sets and nicely behaved because they're closed sets, and a consequence of that is that the utility function will always have a maximum element, an alternative that maximizes U on any compact subset of the set X of alternatives, including, of course, the whole set if it's compact. And then some additional consequences, if the utility function is in fact differentiable, then it'll have partial derivatives, and that will enable us to define marginal rates of substitution and to define the gradient of the utility function, and that's going to enable us to use calculus-based tools to derive implications about the behavior of the decision maker. Calculus-based tools, optimization tools, for example, like the Kuhn-Tucker conditions, there's the envelope theorem, implicit function theorem. All of those tools become available to us if the utility function is differentiable. And as I said, that enables us we use those tools to derive implications about the decision maker's behavior. Now, all of these things are good. So, I mean, it looks like we're golden. We're in great shape if we assume that the decision maker uses a utility function to evaluate the alternatives that might be available to him. But there is one big problem here, and that is that people don't actually have utility functions. It's a completely unrealistic assumption. For example, I would be willing to bet that when you go to the grocery store and you're trying to decide which items to buy or how many of the various items to buy, I'd be willing to bet that you don't consult your utility function to figure out what you're going to do there at the grocery store. You don't, for example, pull out your cell phone and look at the utility function app on there to tell you how many utils you're going to get from the groceries that you buy. And the same thing when you're trying to decide, for example, what courses to take. So, people don't have utility functions. It's a completely unrealistic assumption. And so even though we get powerful tools for making that assumption, we don't want a theory that's built on a foundation of such an unrealistic assumption. So what should we do? Well, how about if we instead just assume that the decision maker uses a complete pre-order, a preference ordering, to evaluate the alternatives, because that is a much more reasonable, intuitively appealing assumption. For example, if we were to ask someone with two alternatives, which one do you prefer? It's pretty reasonable to assume, I think, that the person would be able to say, well, I prefer this one, or I prefer that one, or that I'm indifferent between the two. So this seems like a much better assumption to use than to build a theory on than this unrealistic utility function assumption. But this assumption has a problem as well, and that is that unlike the utility function, pre-orders are not analytically very tractable. They're kind of awkward, clumsy to work with. They just don't provide us with the kind of analytical power, or the kind of tools that we get from functions. So now we kind of have a little bit of a quandary, a little bit of a dilemma here. We could build our theory on utility function assumption, but that's unrealistic. We could build the theory on the pre-order, preference ordering assumption, but that's not analytically very useful. So what to do? Well, remember that when we started with the utility function, we were able to derive a preference ordering, a complete pre-order. Perhaps what we can do is just reverse that idea, just go in the reverse direction. We'll instead assume that the decision maker uses a preference ordering, a complete pre-order, and we'll then use analytically the utility function that's associated with the pre-order. So we assume the pre-order use the utility function instead of assuming a utility function and then trying to use the pre-order. So that idea is a really important idea in microeconomics and game theory, important enough that we actually give it a name and a definition. So here we say that if we have a pre-order on our set X, a utility function for the pre-order, or a utility function that represents the pre-order, we also call it a representation of the pre-order. A utility function that represents the pre-order is just a utility function that, along with the pre-order, satisfies the condition star that we were using in the first place to associate a pre-order with the utility function. Now we use the same idea, the same condition star, to associate a utility function with the given pre-order. But there's a little bit of a problem there, and that is that this definition doesn't actually guarantee that there's going to be a utility function for a given pre-order, unlike the situation when we went this direction, where for any utility function, we knew that there would be a unique pre-order associated with it. Here, we don't know that for any given pre-order, there's going to be a utility function. So that issue arises often in modeling decision-making in economics and game theory, and so we actually have a name for that. We say that the pre-order is representable if there is a utility function representation for it, if there's a utility function that goes along with it. So what we're going to do now is we're going to make a conjecture that, in fact, that in fact preorders are representable. We're going to conjecture that for any complete preorder on our set X, on any given set X, that there will be a unique utility function associated with it, a unique utility function for that preorder, a unique utility function representation of the preorder. And notice, by the way, that now you can see why I titled this lecture Representation of Preferences by Utility Functions, because the underlying problem that we're now going to address is, can we in fact represent preference orders always by utility functions? Now notice that this conjecture is a kind of converse to that proposition P that we started with, the proposition that actually was a remark from a couple of lectures that we did earlier on, that tells us that for every function u here, for every real valued function, we're going to get a complete preorder. And so this conjecture is kind of the converse in the sense that it says for any preorder we can get a real valued function. And so recall that I defined this function pi that takes us from a utility function to the associated preorder. And so here we might say what we're trying to do is we're trying to see if we can define a function that goes the other way. It goes this way, and I'll refer to that function as rho because it gives us representations of preference orderings. So I think this is a good place to take a little break, and then we'll come back for the second half of the lecture where we will determine whether in fact there is a function rho like this that picks out utility representations for given preference orderings. So take a little break and then we'll be right back.